Hello students, have you ever wondered how a projector makes a giant image of a small slide, or how a magnifying glass lets you read those super tiny letters in your textbook? None of these work by guesswork or magic. They all follow the same predictable set of rules through ray diagrams. So, what exactly are ray diagrams? Think of them as the blueprints of image formation. Just like an engineer uses a blueprint to build a bridge without measuring every single bolt, we use ray diagrams to predict exactly where an image will form, how big it will be, and whether it will be real or virtual. Here's the cool part: instead of calculating complex refractions at every curved surface of the lens, we take a shortcut. We use just 2 or 3 special rays, the principal rays. And believe it or not, those few rays are enough to unlock the entire story of image formation. It's like drawing only a few highways on a city map. Once you know those, you can predict how everything else connects. With just a couple of rays, suddenly the whole image appears in front of you. And this isn't just theory on paper. From cameras that capture your selfies, to microscopes that reveal cells, to telescopes that let us look at galaxies, all these devices rely on simple ray diagrams. So in this lesson, we'll walk through these special rays, learn their rules, and see how they can predict images in every situation. By the end, you'll be able to draw ray diagrams confidently and maybe even explain to your friends why their phone camera is just a physics lens at work. Alright students, now that we know why ray diagrams are useful, let's meet the 3 golden rules that make them work. These are the shortcuts that save us from messy calculations and still give accurate results. Rule 1. A ray parallel to the principal axis always has a focus connection. For a convex lens, it passes through the focus on the other side. For a concave lens, it looks as if it's coming out from the focus on the same side. Think of it like this: travel parallel and you'll end up at the focus, no questions asked. Rule 2. A ray that passes through the optical center O of the lens goes undeviated. It doesn't bend at all. Why? Because the tiny bends at both surfaces cancel each other out. It's like being pushed equally from both sides, you just keep walking straight. This rule works for both convex and concave lenses. Rule 3. A ray that goes through the focus F emerges parallel to the axis after refraction. This is simply the reverse of Rule 1, giving us a nice symmetry. So, focus rays and parallel rays are like best friends exchanging roles. And here's the trick: to locate the image of any object, you don't need all 3. Just combine any 2 of these rules, where the rays meet or appear to meet, you get your image. This is exactly how cameras, projectors, and microscopes form sharp pictures, by following these 3 simple ray rules. And once you master them, drawing lens diagrams becomes as quick as sketching a doodle in your notebook. Alright students, let's carefully analyze the case when the object is placed beyond twice the focal length, or 2f in front of a convex lens. What happens to the rays? They pass through the lens and intersect between f and 2f on the other side. So the image is closer to the lens than the object itself. Now let's check the image properties. The image formed is real because the rays actually meet. It is inverted because it flips upside down. And it is smaller than the object. In physics terms, we call it diminished. We can also verify this mathematically using the lens formula 1 by f equals 1 by v minus 1 by u. Here, f is the focal length, v is the image distance, and u is the object distance. Substituting values will always confirm what the ray diagram shows, the image position between f and 2f. Now for the real-world connection, this is how cameras capture photos of distant objects. When you take a picture of a tall building, the lens of your camera reduces that massive structure into a tiny, neat image on the sensor. Without this property of convex lenses, photography as we know it wouldn't even exist. So to sum up, object beyond 2f gives a real, inverted, and diminished image between f and 2f. Or in simpler words, put something far and the lens brings it closer but smaller. Now students, let's place the object exactly at 2f, twice the focal length from the convex lens. This is a very balanced case. Here's what happens. The rays from the object pass through the lens and meet exactly at 2f on the other side. In other words, object and image both stand at equal distances, just on opposite sides of the lens. Let's check the image properties. The image is real because the rays actually meet. It is inverted because once again the lens flips it upside down. And most importantly, it is equal in size to the object, neither magnified nor diminished. This exact principle is used in photocopiers. When you place a page in a copier, the lens forms an image of the text that is the same size as the original. Imagine if the copier got it wrong, one day your notes might come out the size of a billboard and the next day too tiny to read. Thankfully, lenses obey physics, not moods. So to summarize, object at 2f gives image at 2f real, inverted, and equal in size. This is the perfect balance case and a very important one to remember. Alright students, now let's place the object between the focus f and twice the focal length 2f. This is where the convex lens shows off its real magic. Here's what happens. The rays after passing through the lens converge and meet beyond 2f on the other side. So the image shifts further away from the lens compared to the object's position. Now, let's analyze the image. It is real because the rays actually meet. It is inverted because the lens flips it upside down. But here's the exciting part, it is magnified. In fact, the closer you bring the object towards f, the larger the image grows beyond 2f. This principle is the foundation of projectors and microscopes. A tiny slide in a projector can produce a massive image on a cinema screen. Similarly, a specimen placed close to the lens in a microscope appears huge, allowing us to see details invisible to the naked eye. Without this property, we wouldn't have either the science of microbiology or weekend movie nights. So to summarize, when the object is between f and 2f, the image is formed beyond 2f and it is real, inverted, and magnified. This is the case that makes lenses the true enlargers of the optical world. Alright students, let's finish with one of the most useful cases of a convex lens, when the object is placed between the optical center O and the focus f. What happens here? The rays emerging from the object enter the convex lens and diverge after refraction. But if we trace these diverging rays backward, they appear to meet on the same side of the lens as the object. And that gives us a very different type of image. The image is virtual because the rays don't really meet, our eyes only think they meet. It is erect, meaning it stays upright. And best of all, it is magnified. This is exactly how a magnifying glass works. Place a small text or object between O and F and suddenly it looks bigger and clearer. Reading lenses use the same idea, helping people see tiny letters in books or newspapers. Without this property, detectives in cartoons wouldn't have their signature oversized magnifying glass. So, to summarize, when the object is between O and F, the convex lens produces a virtual, upright, and magnified image on the same side of the lens. And that's what makes convex lenses not only scientific tools but also everyday helpers in reading and observation. Alright students, now let's shift our attention to the concave lens, also known as the diverging lens. Unlike its convex cousin, which had many different cases depending on where the object was placed, the concave lens keeps things simple. No matter where you put the object, the result is always the same. Here's what happens. After refraction, the rays diverge. They spread out as if they never want to meet. But if we extend these rays backward, they appear to come from the focus on the same side of the lens as the object. This means the image is always virtual because the rays don't really meet. It is always erect, upright, not inverted. And it is always diminished, smaller than the object. So yes, the concave lens is very predictable. It doesn't like surprises. Now let's link this to real life. Concave lenses are widely used in spectacles for myopia or short-sightedness. People with myopia can see near objects clearly but struggle with distant ones. The concave lens diverges incoming rays so that the eye lens can bring them into proper focus on the retina. In a way, it gives your eyes a little correctional nudge. So, to summarize, for a concave lens, the story is short and sweet. Any object, any position, the image is always virtual, upright, and diminished, appearing on the same side of the lens. Alright students, time to wrap things up with a big picture summary of ray diagrams for lenses. Let's start with the convex lens, our versatile all-rounder. Depending on where you place the object, the image can change in fascinating ways beyond 2F. The image is real, inverted, and smaller. Perfect for cameras capturing distant objects. At 2F, the image is real, inverted, and same size. That's the principle behind photocopiers. Between F and 2F, the image is real, inverted, but magnified. This is why projectors and microscopes work. Between O and F, here's the special one. The image is virtual, upright, and magnified. That's how magnifying glasses help you read small print. Now compare this with the concave lens, which is far more predictable. No matter where you place the object, the answer is always the same. The image is virtual, upright, and diminished. That's why concave lenses are perfect for spectacles correcting short-sightedness. So, here's the big takeaway. The convex lens is like a shapeshifter, sometimes shrinking, sometimes enlarging, sometimes flipping, depending on the object position. The concave lens, on the other hand, is steady and reliable, always giving a smaller, upright virtual image. And that's the beauty of ray diagrams. With just a few simple rules, we can predict the behavior of lenses in cameras, projectors, microscopes, telescopes, and even your own spectacles.